Okay, a very good day to Dr. Siti Rahayu. Today I, Avvinash and Thiyagarajan, will be doing a presentation titled A Study on the Use of Complete Randomized Block Design in Laboratory Experiments. So this would be my presentation outline, Doctor, just for your information. So let's jump right in. So, a brief introduction to complete randomized block design, CRBD. So, what is CRBD? So, in a CRBD, the experimenter divides subjects into subgroups called blocks, such that the variability within the blocks is less than the variability between blocks. Each observation can be classified by two factors, either fixed, also called treatment, that is deliberately varied, or random, usually called block or replicate. Subjects within each block are randomly assigned to treatment conditions in a CRBD. So, the selected case study, mechanisms of modulation of carcinogens by antioxidants, genetic control of the anti-carcinogenic response in mice. So, diaryl sulfide DS, a substance found in garlic, was administered in 3 daily doses of 0.2 milligram per gram to 8-week-old female mice of 4 inbred strains. So, this is our experimental unit, 8-week-old female mice. And the activity of a number of liver enzymes was compared in treated and vehicle treated controls. So, these are our treatments. So there were 8 treatment conditions, 4 inbred strains times 2 treatments in a factorial arrangement in 2 blocks. The work was started when the MRC toxicology unit was being relocated. Hence, the first block was done with mice housed in a plastic film isolator. The second block was done approximately 2 months later with the animals being housed in one of the new rooms in the animal house. Determinations of enzyme activity were done separately for each block using freshly made up solutions. So the activity of one of the liver enzymes, glutathione S transferase, GST in the mice was monitored. So this is our sampling unit, the GST levels in the mice. So the design of the experiment, as we have mentioned, this is a complete randomized block design with the fixed factors being treatment and strain of the mice, while the random factor is the block, which is the location of the experiment. One factorial arrangement, in one block, it consists of 4 inbred strains times 2 treatments. So altogether, there will be 8 mice. So the next part is important. The randomized decision here is which of the 2 mice of a single strain within the block could receive the treatment and which would be the control. Strains of them. The strains of mice used in this experiment were NIH, BLB-C, A-J, and 129-Ola. Block 1 refers to the experiment conducted with mice housed in a plastic film isolator. Block 2 refers to the experiment conducted approximately 2 months later with the animals housed in one of the new rooms in the animal house. So with this, let's look at the results next. First of all, my apologies, doctor, for not being able to see the title. That is the video settings here. So table 1 shows the GST levels in individual mice in a CRBD experiment in 2 blocks, separated by approximately 3 months. So we can infer from table 1, GST levels in treated mice were higher than the mice subjected to control, while GST levels in block 2 were higher than in block 1. Okay. So what did we see? What did we see over here? GST levels in treated mice were higher than the mice subjected to control, and GST levels in block 2 were higher than in block 1. This is the block effect. So what can we tell is that since the GST levels in treated mice were higher, we can say that the treatment is effective. How about the differences? This could be due to experimental error. The differences in blocks could be due to slight differences in the calibration of instruments or minor differences in reagents and solutions used to assess the enzyme activity. Possibly the animals supplied were of a slightly different age, they had a different microflora, they wanted a different batch of diet, or perhaps the different environment of isolator versus animal room altered their response. However, we must look at the relative magnitude of each observation as we cannot control all these variables. So how do we do that? So there are several ways to determine this. First of all, we can determine the correlation between the 2 blocks. It is observed. Okay, from this figure here, we observe that there is a strong correlation, a positive correlation of 0.88 between the 2 blocks. Okay, so what else? We could also conduct ANOVA, so the analysis of variance. Table 2 shows the ANOVA of the data which we saw earlier in table 1. We know that p-values of less than 0.05 are considered statistically significant, so there is no evidence of strain differences in mean GST levels. However, there is some evidence of a strain by treatment interaction. So if we look at table 2 here, we can see that the p-value for blocks, okay, right over here, is less than 0.05, which means they are statistically significant between both the blocks. This is not the case for strain, and it is also significant. There is evidence of difference between the treatment. However, when it comes to strain times treatment, there is evidence of differences. So this is what we would call a two-way interaction. Why do I say this? In the next slide. First, we say there is no evidence of strain differences in mean GST levels, but at the same time, we also say there is some evidence of a strain by treatment interaction. So we need to investigate this. So from this figure here, it shows the GST levels, the mean GST levels in both control and treated mice of the four different strains. So the first column, or the first bar of under every strain is the control, or the second is the treated. So if we take a look at the strain for NIH, there is no significant difference, as compared to other strains of mice. So, but the thing is this true? Is we need to investigate this further. Okay, so ANOVA makes three assumptions for the data. So when we did the ANOVA, we did it with these three assumptions. First, the experimental units are independent. Are they independent? Yes, because they have been individually assigned to the treatments have been individually assigned to them by randomization. Okay, the variances are homogeneous. Yes. How do we know that? We should look at the first figure over here, which is a residual diagnostic plot. So if the variants are homogeneous, we are supposed to see a scatter of points with no pattern, which is exactly the case over here. So how about the third assumption? The residuals, which is the deviation of each observation from its group mean, must have a normal distribution. So in the second figure, the normal QQ plot, if they have a normal distribution, they're supposed to see a straight line fit. However, there is little deviation, as you can see in points number 1, 8, and 9 over here. So we did not fit all these three assumptions while doing this ANOVA. So also the study also states that the ANOVA of the log transform data differs in that there is no statistically significant strain by treatment interaction. The study also states that since there were 3 tests, applying a Born-Ferroni correction would imply that p-value of 0.05 divided by 3, which is 0.017, should be used, in which case the interaction would not be significant. Why? Because earlier the strain times treatment p-value was 0.028. This is more than 0.017, so which means it's not statistically significant. So what is the conclusion of this case study? The results from the 2 blocks had good agreement, and they are likely to be robust as they were separated by 2 months in a different animal house environment. There was no evidence of strain difference in GST levels, although there was a slight hint of strain differences in treatment response, depending on the scale of measurement. So suppose if this experiment had been conducted on a single occasion using 16 outbred CD1 mice. Let's say if we did this experiment one shot using mice of the same strain, it would have given neither an indication of whether there was a genetic component to the response nor whether the results were repeatable. So from this case study, we have identified several benefits of using CRPD. So the complete randomized block design gave extra information ahead, higher external validity because each block samples a different environment at virtually no extra cost, with some assurance that the results should be repeatable. The experiment can also be split up into smaller bits in order to make it more manageable. This would be useful with large experiments and should help to minimize measurement errors because the work can be done under less time pressure. And compared to a completely randomized design, the CRD, this design reduces variability within treatment conditions and potential confounding. Potential confounding refers to a variable that influences both the dependent and independent variable, causing a spurious association. Spurious association means they are associated, but they are not causally related. So if we remove the potential confounding, we can produce a better estimate of treatment effects. So that is the end of my presentation. Thank you very much, Dr. Siti, for your guidance throughout this semester.